Hi, this is my video lab report for Lab 1, Charged Tape. The purpose of this lab was to investigate electrostatic forces using charged adhesive tape. Specifically, we wanted to determine how much charge is required for one piece of tape to float above another when electric forces balance gravity. We also compared our experimental observations with a computational model created in VPython. To briefly preview the results, we observed that one tape floated above another when the electric force balanced the gravitational force. From this, we estimated the charge on each tape to be approximately 9.8 times 10 to the minus 9 coulombs, and found that only one in several million atoms transferred an electron. The first key principle in this lab is Coulomb's law, which states how charged objects exert forces on each other at a distance. Like charges repel, and the magnitude of this force depends on the amount of charge and the separation distance. The second principle is the gravitational force, which acts downward on the tape and depends on its mass. When the tape floated, it was in equilibrium, meaning that the upward electric force exactly balanced the downward gravitational force. This equilibrium condition is what allowed us to calculate the charge on the tape. To conduct our experiment, we made two U-tapes by charging them through separation with a base tape. Each tape had a length of 0.2 meters, and its mass was estimated using a linear density of 1 gram per meter. One tape was placed on supports, while another charged tape was held below it, and we adjusted the separation distance until the upper tape began to float. The distance at which the tape floated was measured to be about 0.021 meters. In this experiment, the system was the floating tape, which we labeled tape B, and the surroundings included the lower charge tape, tape A, and the Earth, which exerted the gravitational force. Using the tape's mass, we calculated the gravitational force acting on the floating tape using the equation F equals mg, which gave a force of approximately 1.96 times 10 to the minus 3 newtons. Because the tape was floating, the electric force had to equal this gravitational force. Using the measured separation distance and Coulomb's law, we solved for the charge on the tape, and this resulted in a charge of approximately 9.8 times 10 to the minus 9 coulombs. To model the system computationally, we represented each tape as a point charge located at its center. This simplified the complex charge distribution while preserving the dominant physics of the interaction. The program calculated the gravitational force, the electric field produced by one tape, and the resulting electric force on the other tape. These assumptions are reasonable because we were only interested in an approximate value for the charge, not an exact microscopic description. The electric field was calculated using a function based on Coulomb's law. This electric field was then multiplied by the charge on the tape to find the electric force. The program also calculated the number of electrons transferred and estimated how many atoms were present on the sticky surface of the tape. The computational model showed that the electric force and the gravitational force were indeed equal in magnitude, confirming our assumption that the tape was in equilibrium. The model predicted a charge consistent with the experimental value and showed that approximately 6 times 10 to the 10 electrons were transferred. When compared to the total number of atoms on the tape surface, this corresponds to only about 1 electron per several million atoms. Overall, the electrostatic force successfully balanced gravity, allowing the upper tape to float. The experimental observations agreed well with the computational model given the simplifying assumptions used. One important takeaway is that static electricity involves extremely small charge imbalances, yet these imbalances can still produce very noticeable forces. Possible sources of error include treating the tape as a point charge, assuming a uniform charge distribution, and ignoring air resistance. Additionally, handling the tape could cause some charge to be lost, and other environmental factors like humidity may affect how well the tape retains its charge. Now on to the what if and why questions. First, what if the electrons and protons switched charges? Well, if the electrons had positive charge and the protons were negative, the observed behavior would still remain the same. This is because like charges would still repel and opposite charges would still attract. Regardless of whatever labels we assign, the physics really depends on these charge differences. Now, why for this lab was it so important to handle the tapes as little as possible? Well, touching the tape allows the charge to redistribute, especially if you consider that the human body is quite conductive. This causes the tape to partially neutralize, reducing the electrostatic force and potentially even preventing the upper tape to float at all. In conclusion, this lab demonstrated how electric forces can balance gravity and how even a tiny transfer of electrons between the tapes creates enough charge for them to repel and lift one another. Thank you for watching.